Hello, this is CSE 100 Discussion 7. This will be covering Project 1 Checkpoint, Huffman Encoding and Decoding. So an overview of what we're going to be discussing. First, we will be discussing the file structure because there's a lot more to this than there was previously. In previous assignments, you may have only had to deal with one file, whereas here there's a whole directory structure that you may or may not be used to. Then we're going to go over testing and writing test first, followed by Huffman's algorithm to construct a tree and destruct a tree, then building the header naively and compressing it and then also decompressing it, followed by CMakeList files and a little bit of file I/O operations. Recommendations. This will take considerably longer than the PAs that you've completed, so please make sure to start early. Followed by copying and pasting is evil. So this is something my boss used to tell me. But essentially, whenever you copy and paste, you should think about why you're doing that and if there's a benefit. Because there's a good chance that if you're copying and pasting something, you should be creating a helper method. So followed by that, use helper methods. Helper methods are great for so many reasons. If you keep copying and pasting code and making slight modifications, there's a chance you'll run into errors. Whereas if you use a helper method, you can easily test that helper method, make sure it works, and you have a single source of truth for that functionality. And that way, if something goes wrong in your program, you can test that, which you should have already tested before, in which case you know that that's not where your bug is coming from, which is extremely beneficial. And finally, using GDB. GDB is super beneficial, and if you haven't used it, which you should have been, now you're going to really need it. Especially using backtrace for segmentation faults, which will help show you where that segmentation fault is occurring in your program. If you don't know how to do this, please look it up online. You can also look on Piazza, as we've answered questions regarding this. So notes, there are no hidden test cases for the checkpoint, but there are some in the final. This is described in the write-up, but I'm just making you aware of it. And then running GDB, this is how you would run it. It's described on Piazza as well. I know some people were running into issues trying to use GDB. Resources, there's the typical resources of Stepic and the videos and the Piazza frequently asked questions, which I highly recommend you take a look at. And there's also a visualization. Now this visualization, I would say, is more for studying than for fully understanding the implementation of what you are trying to create. So this will show you the Huffman tree. But the thing is it doesn't use our exact way of breaking ties. So it's more just to understand the concept rather than understand specifically what our tree would look like. But I do have some visualizations later on that will help you, that do follow how we're implementing things. So for Project 1 Checkpoint, there are 3 parts. Part 1 is writing tests first. Part 2 is implementing the Huffman encoding tree. And Part 3 is implementing compression and decompression. Now, part 1 for writing tests first, this is just a general best practice and something we want you to get used to doing. You are not required to write tests, but they will benefit you in many ways, such as understanding what your program is supposed to do before you write it, and being able to test your program easily and see when you're running into errors. We will be giving credit for the amount of code coverage you have. But that can only help you if you don't already have 100% for the assignment. You can't receive over 100%. I would suggest looking at the rubric to better understand this. So first, I'm going to go over the file structure. This is mainly because it's a new setup that you may or may not be used to, and I know that some people have been struggling with understanding it.
All right, so I just wanted to go over the project structure very quickly. So you need to create this build directory, and that is where your executables will be. And then you'll be working with the data folder, which just has some examples that you can use. And then source is going to be where the files you need to update are. So uncompress, compress, and then HCnode and HCtree. The bitstream files, these ones, we won't be working with right now. You'll be working with those for your final submission. So that is what source looks like. And then we have test. And test here, we once again do not work with the bitstream ones as we do not need those yet. Those will be used for the final submission. So here are some example ones in the HC tree tester file. You can add your own here, and you can use these as kind of a reference for how you should go about building yours. And then we also have the commands cheat sheet, which could be beneficial as well, just kind of going through how everything works. And then if you haven't already installed everything, which hopefully you have by now, you can look at setup.md. And then we have these solution files as well. But like I said, the main things you're going to be working with, you'll execute things from build, but you don't really need to go into that directory. You can just update the path for the executable you're trying to run. And then source is where you're going to actually be changing those files, as well as test for any tests that you want to create. So that is pretty much it. I just wanted to give you a brief overview of the file structure and what you'll be working with.
Okay, so testing, writing tests first. So I'm just going to show you a few examples and talk about some things we need. I'm not going to go into the testing itself. So how do you test compress and decompress is a question we've gotten. And you can't write tests, unit tests for files with main methods, but we do suggest that to reduce complexity of those files, to write helper methods, and you could put those helper methods in files that are then testable because they don't have a main method. Also for line coverage testing, for the checkpoint, this will only be testing the encoder directory. And for the final, it'll be the encoder directory plus the bitstream directories for the final. Also, shell scripting is your friend. So there's a couple of ways of testing, right? We have our unit tests, but we can also diff our files with the reference solutions that you're provided with to see if our solution matches. So for that, you could just diff the two different files, right, that are created by your version, the compressed one created by your version and the compressed one created by the solution. But you could also write a shell script to run through multiple tests at once and then give you feedback. Shell scripts are great. I think some of you probably learned about them in 15L and may have continued to use them, but just in general, they're great for automating tasks. If you see yourself doing something multiple times, there's probably a way you could automate it, and that's just a good skill set and part of being a good programmer. So this is a good opportunity to test that out, though it's not required, but it'll make it much easier to test, and it's, once again, just a good skill set. So using Huffman's algorithm to construct a tree. An overview of what you need to implement for this is HC node. So for this, you need to implement the comparator operator for the priority queue you're going to be using. And then for HC tree, you need to implement the constructor and destructor, as well as build, encode, and decode. Although encode and decode won't be part of building the tree, but you'll need it for compress and uncompress. What is an HC node? So an HC node consists of count and symbol. So the count represents the frequency of a symbol in the input file you're given to compress. The frequency of the symbol. The symbol represents the symbol that you are working with. And then we have C1 and C0, and those represent the children of this HC node. So C0, you can think of it as having an edge going into it with a 0 on that edge, and C1, you can think of it as having a 1. So they're kind of equivalent to a left and right child. We're just labeling them as C0 and C1, which corresponds to what those edges represent for our encoding. And then we have the parent, so a pointer to the parent HC node. So for the comparator, what we are trying to do is determine the priorities for the priority queue. So comparing two HC nodes, which one is greater or lower, So in our case, lower count has higher priority. And if the count is the same, the HC node with the larger symbol has higher priority. So for this, we highly suggest that you create some tests just to make sure you're doing it correctly, because it can be a little bit confusing to implement. And you should remember to add the comparator when you create your priority queue. So here's an example of how you should do it. You can also follow this link, and it shows the documentation of how you should be adding in the comparator. But if you don't give it access to this comparator for HC nodes, it doesn't know that you want to use it. The priority queue does not have access to it. What is an HC tree? An HC tree consists of the root node and leaves. What are leaves? So the leaves vector is going to have 256 elements. One for every ASCII symbol or value, whatever you would like to call it. And these leaves are going to be the leaf nodes of the tree, right? So it doesn't include all nodes in the tree, just the leaves, which are going to represent the symbols that were in our original file that we're trying to compress. For the tree constructor, we need to initialize a new empty tree. So what do we need to do this? We need to initialize root and leaves. So it's important to remember that leaves is a vector of HC nodes, pointers, and that it should have 256 elements in it, one for each ASCII symbol. Now for building this tree, this is essentially what is given to you in the code, but it's important to remember that for this, you're going to want to use a priority queue, and assuming you pass the comparator, which you should be doing, you don't actually have to worry about the priority at this time, because the priority queue will handle that for you using your comparator, and then you just need to pop off nodes, and you will get the next node with the highest priority based on what we determined priority to mean for these HC nodes. So to understand this, we're going to look at the pseudocode and then walk through an example. So the pseudocode for this, essentially, we're going to start by determining the count of each symbol in the input message, followed by creating a forest of single node trees containing symbols and counts for each of the non-zero count symbols. So essentially here, for every symbol that was in the input message, you're going to create a node for that symbol, an HC node that has the corresponding symbol and the count of that symbol from the input file. And then you are going to add all of these nodes into a priority queue. And from there, you are going to loop until there is only one tree in this forest of trees, which will be your final tree that you've created for encoding. And every time you should remove the two lowest count trees. So in our cases, because we're using a priority queue, you just pop the top two nodes, and those will represent the two with the highest priority at a given time. And then you're going to insert this back into the tree. So essentially, when you create the parent of these two nodes that you popped, you're going to insert that parent back into the priority queue. And then you just keep doing that until the priority queue is empty. And once you're done, you have your final tree, and that is what you'll be returning. So here's an example. I cannot read this fish name, but it is the name of a fish, and there is a picture of the fish for you. So here are the counts of the different symbols for this. So assume we have a file with one line, and all it has is this name of this fish. So we've determined the count of all of these, and that would be the frequencies that you create. Now we're going to create a single node for each of these and put it in this forest of trees. And then we insert all of these into our priority queue. And then we pop the first two elements. Now it's important to remember that C0 is going to be the node that has the higher priority. So because we're using a priority queue, C0 should always be the node that you pop first, and then C1 should be the one you pop second. And then the parent node that you create should have the symbol corresponding to the higher priority node, which in this case will be the one that you popped off first. But the count should be the sum of the two nodes, right? So if you can see, P1 is 1, and so is the apostrophe, but combined, their parent has a count of 2. And then you place this parent back into the queue, the priority queue. And then you just follow this same procedure repeatedly to build your tree. So here I'm just walking you through it. And you can walk through this example on your own as well, just to make sure you have a sense of what's supposed to happen. Okay, so here we have our final tree. And one thing to remember is while we have a symbol for all of these HC nodes, the only symbols and the only nodes we care about are the leaves, right? Those are actually representing our symbols and the encoding that corresponds to it, which I'll go more into in a little bit. Okay, so we're using this bottom-up construction. Why do we always remove the two lowest count trees, and what do we achieve by doing this? Okay, so we're using this bottom-up construction. Why do we always remove the 2th lowest count trees? And what are we achieving by doing this? Because the ones you pick first will end up at the lower level in the tree, their encoding will be longer. So you don't want the first ones you pick to be super frequent characters. So essentially, if I had a file with 100 A's and 100 B's and 100 C's and then 1 D, and I'm trying to compress that file, right? So I want to make it as small as possible. I wouldn't want to have my tree constructed in a way where the A's have a longer encoding than the D's, because I'm only going to have to use that encoding once for the D, but for the A, I'm going to have to use it all of the time. So if that was the longest encoding, it would end up using a lot more space. Okay, so now for the Destructor. I am going to go into compress and decompress and everything, but first, for the deconstructor, what do we need to do? So what is the best way of creating the Destructor? Recurse. So for this, there are multiple ways of recursing and having it work. I'm going to give you an example just for the sake of visualizing it, and hopefully that will help you when you're creating it to make sure you're doing it correctly. So as you can see, you always want to remove the children before you remove the parent. Otherwise, you may lose access to those children. There are multiple ways of doing this, but that's just one way of visualizing it. Now, building the header, this is the naive version of compressing the file that's given to you. So for encoding, doing this compression, you're going to be using sudo compress. That method is in compress, and then encode, which is in HC tree. So the way this works is you're going to scan the text file that's given to compute the frequencies of all of the symbols. Then you're going to compute and build the Huffman tree. And then you're going to find the code for every symbol. And you're going to create a new compressed file by saving some information representing that tree at the top of the file. In our case, it'll actually be at the bottom of the file, though. And so for this, the way we're going to do it, our naive implementation, is going to be having a line for every ASCII character. So our header is going to have 257 lines. The first 256 are just going to correspond to the count of all of the 256 ASCII characters. So in cases where that symbol isn't being used, you would put a 0, or you would put the number of times it is being used. So in order for us to uncompress our program, you need to store information to know how to rebuild the tree that you created. So in order to do this, we first need to know the counts of all of the symbols, and then we need to list the bit encoded data. Okay, so here's an example of kind of the whole process that you're going to be going through. So you're given a file to compress. In this case, it only has one line that is ABC. And then when you compress that file, you are going to have 256 lines representing those ASCII characters and their corresponding counts. So in this case, only lines 98, 99, and 100 have a count of 1, and the rest are 0, because our file consists of only 3 symbols, all different. And then line 257 is going to be the encoding of those bits. So it's going to be the encoding of this file, in this case, ABC. And then when we decompress it, we should get ABC back. If you want a better understanding of how this works, you can run the reference solution a couple of times with different files to try to get a sense of what you should be doing to implement this. So this is the tree we had, and it's important to remember that we have these C0 and C1 children, right? And those essentially represent the child which has an edge of V0 and the child which has an edge of 1. And that allows us to follow this process and encode our symbols. So here's an example of encoding. So for H, right, we're given an H. We can find that pretty easily because we can go up from H or down. I'll explain the way we should be doing this later on. But essentially, you can get each of these through the tree, right? So this is just going through the encoding of this message. I'm going to go through it relatively quickly, but you can go back over this later on your own. Okay, so what role does encode play? So encode is used to encode a given symbol and write it to the file that was provided to have our compression written into, where the header should go. So for this, it's used to build it symbol by symbol. So you should be calling encode for each of the symbols, and this is building the line 257, right? Not the frequencies, but the final line that represents the encoding of the original file. So how do we quickly encode our symbols, right? It would be best if we had somewhere where we were keeping track of the leaves, because that represents the symbols in our tree. So we have leaves, remember? So that's something else you should be creating early on, which is when you're building the tree, right? You want to add in these leaves so that we have access to the leaf nodes and can easily get the encoding for these different symbols starting at the leaves. And this makes it so that we can get our leaf nodes in O of 1 and find their paths. Now decompressing our header. So for this, you're going to read the file header, which would be the compressed version, to recreate the tree. So first, you're going to read the frequencies of the letters, the ASCII values, which will be lines 1 through 256 of the file. And then you're going to decode each letter in line 257 by reading the rest of that file and using the tree that you created. And then you're going to write that to an output file, and that should match the original file that was passed in for you to compress. So here's an example of coding and decoding the file. So this is the encoded message for the word we've been working with. And then as we decode it, right, you can see that these we're walking through step by step, and we're able to get these. And this will just continue until you've decoded the entire message. There's multiple ways of implementing this, but you will use decode. So what role does decode play? It's kind of the opposite of encode. So for this, it's going to decode a symbol. So what it's going to do is it should keep reading from the input file until it's reached a leaf node. And at that point, you have the symbol that represents that next part of line 257 of the message, the encoded message, and then you return that symbol. So essentially for that, right, so decode should be given the file, the compressed file, read from line 257, and read from it, iterating through the tree until it finds a leaf node. And then it should return the symbol at that leaf node. So both decode and encode should be called multiple times, and they're just a part of the compression and uncompression. So now for CMakeList Files. CMake Intro and Demo. CMake is an open source cross-platform family of tools designed to build, test, and package software. CMake is used to control the software compilation process using simple platform and compiler independent configuration files and generate native makefiles and workspaces that can be used in the compiler environment of your choice. So this is something that's typically used at companies. We can make our own makefiles on our own, but this will generate them for us, which is much nicer and something good to understand. Also, you will be creating the CMakeLists file in your final submission. So CMake project. The top level CMakeList file for a project must contain a literal direct call to the project command. This sets the name of the CMake project. So in our case, this is Huffman encoder. And you can see all of this if you look in the CMake files. All of the examples have been taken from the code that you've been given, the starter code. So adding a subdirectory. This adds a subdirectory to the build. The CMakeLists file in the specified source directory will be processed immediately by CMake before processing in the current input file continues beyond this command. So in this case, we are adding our test subdirectory. In CMake, we can use add directory to add in CMake subprojects. So here's an example of adding gtest for our Google testing. Now, add custom target. This allows us to add a custom target, in this case related to our testing, but we could do something like echo hello world. And for all of these examples, I would suggest looking stuff up online. You've also been given a cheat sheet, which is pretty valuable for the CMake. Target include directories. So CMake specifies include directories are targets to use when compiling a given target. The named target must have been created by a command such as add executable or add library. For linking dependencies, we have a couple of ways of doing this. Adding libraries. So we need to do this in order to be able to declare a dependency that does not only include HPP files, but CPP. So here's an example of adding the Huffman encoder, the HC tree. And you should note that the difference between public and private is that with public, the build targets that use the Huffman encoder library can access the header files in this include directory, but with private, they cannot access them. This defines, so add executable defines the set of source files that will be compiled into an executable. You can list dependencies. So here is an example with uncompress. All right, so this sums up CMake. As I said, you should really look this up as well and look at the cheat sheet. It's an extremely useful thing to have and to be used to using. Now for C++ IO IO operation. So here the F stands for file, where it's also an IO string stream, which you'll be using in your unit tests. And there's a more generic IO stream, which can accept both the file stream and the string stream types. And you can combine two or more of these values by ORing them together. I would suggest looking at the test cases that we have provided to you as a starting point. You can also look just for general file operations at the main methods of compress and uncompress, where we've provided you with some code to get you the files you need to access them and read and write from them. So here's a simple example of reading the code. What would you expect this to produce if we ran it? So here, if the file exists, then it will write hello world to it. Otherwise, it'll create a new file by that name and write the content to it. So this is something that you may want depending on what you are trying to do. All right, so that is the end of discussion. If you have any questions, please post them on Piazza. There are a lot of resources for you. I personally really enjoyed this project, though I know that there is a lot to it. So you definitely do need to start early. But I hope you enjoy.